Okay. Okay, to determine if the function is increasing or decreasing, first we want to look at the domain. And we want to find the velocity function, which is finding dy dx. Find the critical points. Okay, when the velocity function, or dy dx, equals 0, what does that mean? You have, well, yeah, you have a max or a min, though. And, or we're also looking at when dy dx is undefined. Okay? Part D, we'll use a number line to find where we're increasing and decreasing, or where the velocity function is positive and negative. Use a number line to find where dy dx is positive and negative, and then we'll get the answer. Okay, so number 1, part A, we have a nice little polynomial. This is a cubic function. You need to know your parent functions. What's the domain of a cubic function? All real numbers. Domain is negative infinity to positive infinity, or you could say all real numbers as well. Part B, we're going to find dy dx. Dy dx means take the derivative. Okay, Ariel, can you tell me what the derivative of this would be? Great, and now it becomes a quadratic function, right? Okay, so we have dy dx. Now let's find the critical points. I'm going to put CP for critical points. How do we find critical points of a quadratic? Yeah? Factor end, set equal to 0. So does this one factor out nicely? 0 equals x and x, two numbers that multiply to negative 15 but add to negative 2. It'll have to be negative 5 and positive 3, right? So our critical points, therefore, will be x equals positive 5 and negative 3. That's where the quadratic crosses the x-axis, right? Which means they'll be, they have a slope of 0, so that's a max or a min on our position function. Okay, so just a quick sketch to help us visualize what's going on. Here is 5. Here is negative 3. Is our quadratic positive or negative? It's positive, so it's concave up. Which means here, our velocity function is positive. Here, velocity function is negative and positive. Okay, so part D, let's use a number line to find for dy dx. Our critical points are negative 3 and 5. From negative infinity to negative 3, is the dy dx positive or negative? Positive. Which means the position function is increasing. And then from negative 3 to positive 5 is negative, which means the position function is decreasing. And then after that it becomes positive again, which means the position function is increasing.
The bottom is what the original thing.
Yep. Okay, and now let's see, get our answer, which is the intervals at which we're increasing or decreasing. F is increasing on the interval of negative infinity to when? Negative 3. What happens at negative 3? So do I do a parenthesis or a bracket? Parenthesis, because it's actually changing between increasing and decreasing. Okay, union 5 to infinity. And that is because f prime is greater than 0. Or y prime, okay, dy dx is greater than 0. It's positive. F is decreasing on what interval? Good. And what type of brackets and parentheses go around negative 3 to 5? Parentheses. And we can say because, we know this because what? F prime is less than 0. Okay? All right. Let's look at number 3. If you flip it over to number 3. Okay, the derivative. Well, the derivative of this one's, no, this is part A. Not derivative, domain. Domain of this one is not as easy because it's a rational function, not rational. Yeah, rational. Radical and rational, those sound the same. Rational function. Is there anything that can't be in the domain? Any x values? We can factor that, right? We get x minus 2 plus 2. Do those cancel? Are they removable discontinuities? No. So if they're non-removable, what happens? Not a whole. Removables are whole. Vertical asymptote. X equals negative 2 and positive 2. So our domain goes from negative infinity to negative 2 union negative 2 to positive 2 union, all parentheses because we have vertical asymptote, 2 to infinity. Okay, part B was take the derivative. So k of x, the derivative of k of x, how would I notate derivative of k of x? K prime of x. Ho-de hi minus hi-de ho over ho-ho, right? Ho d hi, what's the derivative of the high? 1. Minus hi d ho, what's the derivative of the low? 2x. All over ho-ho. X squared minus 4 all squared. Okay, so to keep equivalent statements, I'm going to put an equal sign right underneath it. This becomes x squared minus 4 minus 2x squared. Correct? Any questions about that? The denominator stays the same. Now I can simplify. I have like terms 1x squared minus 2x squared would be negative 1x squared minus 4 over x squared minus 4 all squared. Now, if I pull out a negative sign, would I have something that could cancel? No. It'd make it a plus 4 if I pulled out a negative sign. So I can't cancel. So that's my derivative. And the reason we find this derivative is we're looking for critical points when the derivative equals 0. Okay? And places where the derivative is undefined. So for critical points, if I set, for part C, if I set this equal to 0, does the denominator matter at all? If I times the denominator over to 0, doesn't it just go away? So with critical points, you're really only looking at the 0 set equal to the numerator. Set the numerator equal to 0. If you solve that, where would our dy dx derivative graph cross the x-axis? If If I add 4, 4 equals negative x squared, divide by negative 1, I get negative 4 equals positive x squared. Can I take the square root of a negative 4 in our real numbers? So this will be, there are none. Critical points, there are none. What about restricted values? Restricted values, when the denominator can't equal 0. The restricted values are when the denominator can't equal 0. What number squared minus 4, all squared would be 0? Okay, if you don't know, then set it equal to 0 and solve it. Because it'll end up being plus and minus 2. So x can't equal plus and minus 2. Those are restricted values because it will make the denominator 0. Okay, so that was part C. Part D is now take this stuff to a number line. We're looking at K prime. You should be labeling this line. What critical point should I put on my line? -2 and +2. Now you have to figure out what's happening with the derivative function, if it's increasing or decreasing. So looking at this derivative function, we want to know what's going on at negative infinity on the left side of -2 and positive infinity, right, on the right side of -2. So if you're looking at the infinities, what could you look at? We've done this before with limits. When you're looking at M behavior models. Okay, so if I did a little M behavior model here, K prime of x would be essentially negative x squared over x to the 4th, which becomes negative 1 over x squared. So anything you plug into the function is going to be squared, which makes any x you plug in has to become positive, but there's a little negative sign, so everything will be negative, 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 which means the entire position function was always decreasing. Okay, so for E, our answer, K is decreasing on all real numbers. Is that what I should put? Right. We have restricted values, -2 and +2. So it'll be negative infinity to -2, union -2 to 2, union 2 to infinity. Because K prime is greater than 0 or less than 0? Less than 0. Okay, I have a new little pink slip for you with homework. The Let's See is due on Tuesday.
So we'll have questions on 5.2 next time?
Yeah, we can do questions on both that we didn't do today. 5.2 next time, and a lesson from last time you can bring questions on, okay? So we didn't do it today. But also be prepared for another 100% derivative test. I'll put the answers to that big blue packet on my website.